Okay, we are talking about chapter 9 and solutions here. So last time we talked about solutions, and remember, as we talked about, there are two parts to a solution. There is obviously the solute, which is the smaller part, and there is the solvent, which is the larger part of the solution. So typically, as we talked about, the solute is oftentimes the sort of substance that is a lot of times dissolved in the larger part, like the solvent. For a lot of solutions, the solvent is water. It's a really good solvent, as we talked about, for things that are ionic, for things that are polar. And as we talked about, really things do mix together well to make a solution when they do have very similar sort of intermolecular forces or ways to interact with each other that are very, very similar to how they interact with really themselves. So we talked a lot about last time as well, the idea of like dissolves like. So, things that are ionic and polar work really well together. Things that are polar and polar will also work really well. And again, also things that are nonpolar and nonpolar, those things actually do mix really well together. It's really just when you cross over from something that is polar and something that is nonpolar and put them together. Again, I think we talked about oil and water and some other sort of interactions, but really they do not have a long way to continue that interaction with one another. So they typically do not mix sort of to make a solution. We talked about a couple of things as well. We talked about electrolytes. And remember, electrolytes are really substances that, when they kind of go for a swim in water, will break apart into ions. And it's really the presence of these ions that helps sort of conduct electricity. There are things that are strong electrolytes, which when they do go for a swim, essentially will 100% break apart. So something like sodium chloride solution. If you have sodium chloride that's dissolved in water, it is a very strong electrolyte. It will 100% break apart into sodium ions and chloride ions. You will not have any of these sodium chloride units still together in that solution. They will all 100% have broken apart into really the cations and anions. And that's really why it's a strong electrolyte, because it really produces a lot of ions in that solution. And it's really the ions there that, as I mentioned, what helps conduct electricity. So I think we talked about sort of the light bulb example, and I think maybe this week's experiment used the light bulb sort of a thing. Yeah. So on some of those that she probably put into the light bulb, or today when you go to lab, she puts it into the light bulb, it will go off very, very brightly. And those are really strong electrolyte solutions. They 100% dissociate into ions. And that's really why, it's able to sort of turn the light bulb on very, very brightly. There's also weak electrolytes, which, unlike strong electrolytes, when they go for a swim really in the solution, they actually tend to stay together. But they do and are able to basically produce a little bit of ions. So even though for the most part they will kind of stick and stay together, they will still be able to sort of break apart a little bit, produce a few ions in solution. You oftentimes can recognize the weak electrolyte equation with the arrows that you see, which are typically those two arrows heading in both directions. And because it's still able to sort of break apart into a few ions in that solution, it's still able to conduct electricity, but it cannot conduct electricity anywhere near like a strong electrolyte could. So again, for some of you, we'll see it today. And for others, you probably also saw some when she put it in there. The light bulb went off, but it was very dim, the light bulb. It wasn't as very bright as, say, in a strong electrolyte. And that's really because the presence of ions in that solution is a lot less than it is in a strong electrolyte. And then there's some things that are non-electrolytes, which are things like, for example, sugar, which are covalent molecules or molecular compounds. They will dissolve. So we know if we take sugar, and as we talked about also earlier in this chapter, the reason it's able to dissolve in something like water is sugar has a lot of OH groups all over it. So it allows it to interact really well with water. But something like sugar will dissolve. The difference is, though, it will not produce really any ions. And because it doesn't really produce any ions, it really will not conduct electricity. So again, there should probably have been some as you put it in there and the light bulb didn't go off. Those would be obviously strong, non-electrolytes. in that particular case. And maybe it's been so long since I did that lab, but they used to also show you the difference between sodium chloride that's in a solution form and just solid sodium chloride. So sometimes they put the thing in the solid sodium chloride and it doesn't go off. And again, it's because in solid sodium chloride, the ions are together still. It's really still sodium chloride together. But once you dissolve that in solution, the ions again are liberated and 100% break apart. And again, that's at that point when the light bulb would go on. We, in addition, talked about equivalents. And equivalents are really related to the charge. And we really get sort of a conversion factor from it. So something like sulfate, which has a -2 charge. Talked about the actual sign of the charge is not really important in this application. It's actually just the number. So here that's a 2. So we could say 1 mole of sulfate gives you 2 equivalents. And we oftentimes will use this in a sort of conversion factor as one way things like IV bags and stuff like that used to be labeled. Also used to be part of the lab. They give you some empty IV bags with some labels, I think. Yeah. So one sort of concentration unit that's commonly used is equivalents per liter or milliequivalents per liter. So those are 2 common sort of units of concentration. And we went through some calculations last time, and a reminder that, you know, when we take something that's ionic, we do balance out the charge. And since really equivalents are based on charge, what we do end up seeing is if you had, I think we looked at maybe sodium sulfate maybe the other day. And if you look at something like sodium sulfate here, it's really made up of 2 ions, sodium and sulfate. And because we really do balance out the charges in there, what we end up looking at when we look at something like equivalents per liter or milliequivalents per liter is we actually end up with the same sort of concentration for each of those ions, the positive guy and the negative guy, because they should technically always balance each other out in that solution. So again, because really the equivalence part of that concentration is based on charge, we do end up with really the same numbers for each of those ions, the positive guy and the negative guy. We finished up at the very, very end talking about another concentration unit, which was percent mass to mass. And that is the mass of the solute divided by the mass of the solution times 100%. And this is sort of a percentage concentration. And the important part here, especially with this one, as we talked about, is really the bottom part here. It's very common in these problems that they will sort of give you the mass of the solvent and the mass of the solute sort of separate from one another. So a lot of times you do need to add those numbers together. I think like the very last example we did there when we finished up, to make sure that you really do get the mass of the actual solution. It's a very common mistake that people make is they end up dividing by kind of just the solvent because they look at it and go, that looks like the larger number, so we'll go with that. But you oftentimes want to make sure you do have to get the mass of the solution on the bottom there. Any questions on any of that stuff we talked about last time? Okay. So then let's take a look at another example here, mass percent, see what you come up with. Concentrated hydrochloric acid solution contains 37.2% by mass. Hydrochloric acid, what is the mass of the hydrochloric acid that's contained in 35.5 grams of the concentrated hydrochloric acid solution? All right, take a couple minutes, see what you come up with on that. Let's take a look at it. And there's really a couple of different ways you could solve it if you like. Obviously, it's a percent mass to mass. So we could use our formula here, percent mass to mass is equal to our mass of the solute divided by the mass of the solution times 100%. Remember as well that if you're not sure what the solute is, it is really the name of the solution. So if we have a hydrochloric acid solution, then that is the solute, which means if we are looking for the mass of hydrochloric acid, we're actually looking for the mass of the solute in this case. So that's again how you can kind of figure that out. We could also sort of approach it more like dimensional analysis and using a conversion factor. So I think we also talked about the other day that when you do have sort of a percentage by mass, you could really turn it into sort of a usable sort of conversion factor, if you will. And we could do that simply by assuming really like 100 grams, in this case, 100 grams of solution. So if we assume 100, what that means, if we have 37.2% by mass, that would mean we would have 37.2 grams of HCl and 100 grams of solution. Or again, we could use it sort of the opposite way. 100 grams of solution would contain 37.2 grams of HCl. So we essentially can kind of turn that percentage into a couple of conversion factors that we could use. And since we know we are starting with 35.5 grams of the solution, we can use the conversion factor here on the left. And if we do that, that would give us 100 grams of solution times 37.2 grams of HCl. The grams of solution will cancel and we will be left with like 13.2 grams of HCl in this case, which is our mass of our solute. Any questions on that? So if we have a percentage, you could assume 100 of something. So in this case, since it's mass to mass, we can assume that we have 100 grams of the solution. You could really assume any number you want, but the reason obviously that we assume 100 is because it keeps the number the same, the percentage number the same. You know, if you did 200, you would have to double that number and you do a lot more math. So that's why we usually assume 100 of something, and it keeps the percentage number basically the same. You could just kind of convert it to the units that you want. Other questions? Now, you know, you could plug and chug into the original formula, which obviously would be 37.2%. is equal to the mass of the HCl divided by 35.5 grams times 100%. And basically what you're going to do mathematically is exactly what we just did here. You're going to divide the 100 to the bottom, and you're going to multiply 35 to the other side. And mathematically, you end up doing the exact same calculation, obviously, as what we did above. But if you want to plug and chug into the formula and rearrange it, you can absolutely do that. Obviously, it would give you the same answer as kind of doing the dimensional analysis way. Any questions on that there? Okay. All right, so that is mass percent. There's also a couple of other sort of percent concentrations that we commonly sort of use for solutions. One is sometimes referred to as volume percent, like in alcohol, percent by volume, that type of stuff. And it's sometimes abbreviated percent volume to volume, or V to V. And this is the volume of the solute over the volume of the solution times 100%. So these are actually volumes. And the good news on these type of problems is they typically just straight up give you the volume of the solution if they give it to you. So unlike the sort of mass one, where it's commonly sort of separated out the solute and the solvent, usually in sort of this problem, it's really not separated out. So you don't have to worry, usually in most cases, too much about that. And we could also sort of convert this just like we did in the previous problem we talked about before, that, you know, if you had a percent by volume, say 3.5% volume to volume sodium chloride, you again could just take that and put it into a conversion factor. If we assume 100 milliliters in this case, that would mean you had 3.5 milliliters of sodium chloride and 100 milliliters of solution. So again, that's a way you could kind of take the percentage like we just did sort of in the previous problem and convert it into a usable conversion factor. You obviously could also do the opposite of it, which is 100 milliliters of solution if you needed it sort of reversed, 3.5 milliliters of sodium chloride. So sometimes people like to take more of a dimensional analysis approach with these problems, especially if you're given the percentages rather than sort of rearranging the equation, so you can still kind of see the units and cancel things out. So we sort of think of volume to volume a lot of times as really milliliters per milliliters, but it could really be liters and liters on the top and bottom. As long as they're really the same unit up on top and up on the bottom, you know, it would work out okay. But most of the time we deal in milliliters, so that's very commonly what we sort of think about in terms of the units on these. Any questions on that one there? The last sort of percent by volume type of calculation, or percent calculation, concentration is mass to volume. And this is, again, sometimes abbreviated percent mass to volume. And that's what the M and the V stands for. And this is basically the grams of the solute divided by the milliliters of solution times 100%. Kind of like a density value, right? Density is like grams per milliliter, right? It's sort of the same idea. It's basically how many grams there are like in a milliliter. And just like all the other two sort of percent concentrations, we also could turn this guy into a usable conversion factor. Same idea. This would be 3.5 grams of sodium chloride in 100 milliliters of solution, or obviously, again, the flipping version of that there. So these are three very common sort of percent concentrations that we sometimes come across in solutions. In terms of the answer at the end, a lot of times we really don't use units per se, but we do use sort of what it is. So if we were to solve for the percent mass to volume, you know, this is sort of the units that we would sort of put at the end of it, obviously along with the number and maybe what it is, sodium chloride, calcium chloride, whatever the actual solution would be. Any question on any of those three there? All right, so why don't we try one here? What is the mass to volume percent of bromine in a solution that's prepared by dissolving 12 grams of bromine in enough carbon tetrachloride to make 250 milliliters of solution? Okay, so taking a look at this one, we are looking for the mass to volume, which again means our percent mass to volume is the mass of the solute divided by the volume of solution times 100%. In this particular case, the Br2 is our solute. And in this particular case, it is the carbon tetrachloride that is our solvent. But in this case, they did give us the straight volume of solution, so that's all taken care of for us. So we could just put it in. We'll take our 12 grams, we'll divide it by 250 milliliters, times it by 100%. And that would get us 12 divided by 250 times 100. Looks like 4.8% mass to volume. Br2 would be our answer here. Question on that one. So my question is, why did we not use water as our solvent here? So our solute is Br2, right? And if we throw back to old school Lewis structuring there, Br2 is what type of molecule? Is it polar or nonpolar? It is nonpolar, right? They're both bromine. It's diatomic. There's just one bond there, which means this is a nonpolar molecule, which means if we tried to use water, which is a polar molecule, as our solvent, those two guys are going to have a very hard time interacting with each other, because really water is going to want to use hydrogen bonding, and the bromine there wants to use actually what's known as dispersion forces. And it's kind of like oil and water. That's really not going to mix. So you actually see two layers if you did this. You might have did it in lab. So when we look at something like carbon tetrachloride, which just looks like this without all the dots. But if we look at this, this is one of those symmetrical geometries we talked about. There's no dots on the central atom. Everything on the outside is the same, which means this guy should be polar or nonpolar. It should be nonpolar. So remember, no dots on the central atom, everybody on the outside the same, should give you equal distribution of the electrons and should be a nonpolar molecule. That means we just mix basically a nonpolar molecule with a nonpolar molecule. And if you think about what we were talking about, like dissolves like, that is good. Yes, those things are going to be using the same type of interactions with one another, and they do mix really well. So as I mentioned earlier, water is used in a lot of situations but it's not always the right thing to use as a solvent, especially not the right thing to use if it's a non-polar solute, because they 100% will not mix together. Any questions on percent concentrations, solubility of that? Okay, so one last one here. Calculate the grams of KCl and the grams of water in a 225 grams of an 8% by mass. You can read it. Mass to mass KCl solution. I butchered that pretty good there. So it says something like that, I think, but you know. So basically there's 225 grams of a KCl solution that has a concentration of 8% by mass. That's what I was trying to spit out, I think. All right, take a couple minutes. You should be looking for two answers. What is the mass of these KCl? And what is the mass of water in this solution? So obviously we're dealing with percent mass to mass, which is our mass of the solute divided by the mass of the solution times 100%. We also know, as we talked about before, that the mass of the solution is equal to the mass of the solute plus the mass of the solvent here. So in this case, the KCl is obviously our solute, as it is basically the name of the solution. Water here, which is a very common solvent. So that is basically what we're looking for in this particular case. We can approach it kind of like what we did before. We could just find the mass of the solute right off the bat. Again, I'm going to kind of do it more dimensional analysis way. So what we have here is 8% by mass KCl. What that means is we have 8 grams of KCl and 100 grams of solution. Or again, we could kind of use it the other way if we need to. 100 grams of the solution would contain 8 grams of KCl. In this particular case, they gave us the mass of the solution, which is the 225 number there. So we'll start with that, the 225 grams of solution. Obviously, here we would then want to use our conversion there on the left, so everything cancels out correctly. And that's going to give us 8 grams of KCl, 100 grams of solution. Those guys are going to cancel. And I want to say 18. Let's see, 225 times 8. Does that sound about right? Good. That gives us 18 grams of KCl in this case. First off, any questions on that? Okay. Now, sig fig wise probably should be 18.0. We'll pop the 0 in there. This is KCl, which is our solute here, right? And that means that we are looking for really the water, which is our solvent. So that's really where this relationship could come into play. We obviously know that we started with 225 grams of the solution. From our calculation, we just got the mass of the solute, right? So we could rearrange that and find that the mass of the solvent, also known as water in this case, would be the mass of the solution minus the mass of the solute. So that would be a 225 minus an 18, and that would get you about 207 grams of water would be in this particular solution. Again, if we take the 207, obviously, and add it to the 18, we get our 225, right, which is the mass of the entire solution, made up of basically 18 grams of KCl that you took basically and dissolved in 207 grams of water. Any questions on any part of that calculation? Yeah. Yeah, so in this case, we had to rearrange that. So let me maybe back right there. So this is the relationship for the solution, which is the mass of the solution is the mass of the solute plus the mass of the solvent. And in this particular case, we actually want to find just the mass of the solvent by itself, which is the water, because we actually knew the numbers for the other two. So basically we had to subtract the mass of the solute to both sides. And that's how it goes away on the right-hand side, and it becomes the mass of the solution minus the mass of the solute in that case. So it's just rearranging that sort of relationship based on the numbers that we were given. Other questions?
You have to take both answers. The 18 grams, so you have 18 grams of KCl and 207 grams of water.
In that particular problem, you would need two answers because it asks for, if that's your question, it asks for what is the grams of KCl and what is the grams of water. So you would need both answers for that one. Yeah. Obviously, like a previous problem, if it just adds, for example, just the grams of the KCl, then we could have just stopped at the 18 calculation. But because it wanted to know basically how much water, which is a solvent, we had to get the other calculation. Yeah. Other questions? Okay. So those are our percent concentrations, and this is a table, I think, from your book as well. And again, it really talks about what we were doing here in some of these problems and sort of how I worked them out, where you could take any type of those percentage units and really turn them into a conversion factor. And, you know, sometimes it's a little bit easier for people to do it that way because you can kind of see all the units and just kind of just do it like a unit sort of problem where you're getting rid of the ones you don't want, kind of keeping the units you do want. So it's a good approach, but as we also talked about, if you want, you could just plug and chug into the formula and rearrange it correctly, and obviously you'd end up with the same answer. So it really is just a preference on how you might want to kind of solve those problems. Any questions on any of those percentages, type concentrations? Now that we talked about the percent concentrations, we're really going to talk about the, you know, the big concentration unit that really is most commonly used with solutions, and this is molarity. Molarity is abbreviated with a big M, and the big M does stand for really moles of solute divided by liters of solution. And most often people just go moles per liter in that case, but that's really what those sort of units represent. And it is sort of an equation that you should think about as something that you can rearrange. And we could rearrange molarity a couple different ways, and we do use it a lot in chemistry. First off, we do calculate the molarity, obviously, by taking moles divided by liters. And again, in terms of what the number represents when you see it, typically the larger the number associated with molarity, it is much, much more concentrated. So if you ever played with anything that was like 18 molar hydrochloric acid, that is extremely highly concentrated, like open the bottle and fumes come out, so concentrated. As opposed to if you use like 0.1 molar hydrochloric acid, that is much, much more dilute. So in lab, be careful of things with very big numbers in front of the M. They are very strong in most cases. We could think of this kind of like the density equation, if you will. We oftentimes do rearrange it to solve for any one of these three things. So if we wanted to solve for liters, that would be moles divided by molarity, multiplying the liters to the left and dividing by the molarity. And also a very common way that we sort of rearrange this equation is to actually solve for moles, and moles would be equal to liters times molarity. So those are three ways that we very commonly kind of use molarity and sort of manipulate it to find things like volume, to find things like moles along the way. When we do say we have a solution that is a particular molarity, we do want to, a lot of times, kind of get rid of the big M in calculation. I think I might have talked about it the other day as well a little bit, but if we did have something like 4.5, big M is referred to as molar, say sodium chloride, a lot of times people will leave the big M when they kind of do calculations, and it's very common that people have really no clue or remember that there actually is like the liters component to molarity, and they oftentimes forget all about the volume part of it and things like that. I highly recommend in a lot of calculations that you really ditch the big M and you can convert it into almost like a conversion factor. What that really means is that you have 4.5 moles per liter of sodium chloride. The number always stays with the moles and it's always 1 liter. So that's how you could kind of convert molarity into a usable sort of number, because when we look at the way we wrote it here, we could clearly see obviously both units. So hopefully that will remind you, oh, there is like liters involved there and where it is. And we could think of it like a conversion factor, like moles are on top, liters are on the bottom. And you could treat it like a conversion factor. You could divide by the molarity, which you would put liters up on top and moles on the bottom. So you can really use it very much like a conversion factor. Obviously, in the top way here, we would be multiplying by that number. The bottom way here, we would technically be dividing by the number. But it is very helpful a lot of times to really pull that big M out of there and replace it with both of those units. So just visually, as you're doing the problem, you keep track that there are two different units and sort of where they are. And again, it's just a very common thing that people just leave the big M. And honestly, they end up thinking just about moles a lot of times and not even thinking about the volume part of it. So I would highly recommend getting rid of the big M, doing a little bit more like a conversion factor dimensional analysis way so you can kind of see the units. And it really is oftentimes very beneficial. Now, when we talk about molarity, it does mean a couple of things. It basically means that we have 1 mole of solute per liter of solution. So if we had a sodium chloride solution that was 1 molar, what that means is we would actually have 1 mole of sodium ions and 1 mole of chloride ions. And the concentration of those ions actually would also be 1 molar for the sodium guys floating around and 1 molar for the chloride guys floating around. When you look at an ionic compound and you look at concentration like molarity, it works kind of like, you could think of it like stoichiometry. And what I mean by that is if this whole thing was 1 molar, if we were interested really in just the sodium ion part of it and what the concentration of sodium ion is, we could think of it as for every one of these, we get 1 of those. So you basically just multiply the concentration by 1 and you end up with 1 molar for the sodium ion would be the concentration. Same thing, it's a 1-to-1 relationship between the chloride ions and the whole thing, which means technically it would be a 1 molar concentration for the chloride. Concentration is not additive, so clearly if you add 1 and 1, you get 2, right? And it doesn't equal 1, but it's sort of the proportion of what's floating around in that solution to the whole solution is what we're looking at here. And the sort of long calculation of that really is the stoichiometry part of it. So for example, if we started with 1 molar sodium chloride, that really is 1 mole of sodium chloride per liter. And if we were looking at the sodium ion, it is stoichiometry a 1-to-1 relationship, which means we are technically taking 1 mole of the whole thing is 1 mole of the sodium ions. Those guys cancel, leaving us 1 mole of the sodium ions per liter are 1 molar sodium ions. And that's why we multiplied by 1. Now, what happens if I had, say, calcium chloride here that was also 1 molar? When this guy would break apart, it would break apart into a calcium ion, right? And how many chlorides? You would get 2 chloride ions, right? That's what the little 2 there on the bottom means on the left. Now, the concentration of calcium is still a 1-to-1 relationship, right? Which means the calcium ions in that solution would also have a concentration of 1 molar. But what is the relationship between calcium chloride and chloride? It is a 1-to-2 relationship, which basically means for every one of those calcium chlorides that go for a swim, you get twice as much chlorides floating around, right, than you do calciums. So what we actually do is just multiply the molarity by 2, right? We kind of double it. So the concentration of chloride here would actually be 2 molar for just the chloride ions. And that's the quick way that you could do it, is simply, it's a 1-to-2 relationship. You take the concentration and multiply it by 2. So 1-to-1 relationship, you multiply it by 1. If it happened to break apart into a 1-to-3 relationship, you would multiply it by 3. The long version of that calculation is this. You would start with 1 mole of calcium chloride per liter. And we'll just do this guy. Between this guy and this guy, it's a 1-to-2 relationship, which means for every 1 mole of the whole thing, you get 2 moles of chloride. Moles of the whole thing cancel. Leaves us our 2 moles of chloride per liter, which is the same thing as 2 molar of the chloride. So when I said this is a 1-to-2 multiplied by 2, that's really why you multiply by 2. That's taking the stoichiometry sort of relationship into account. So sometimes in sort of solution problems, you may not be interested maybe in the concentration of the whole entire thing. You may be interested sort of in maybe one of the ions that are floating around in the solution. And we could actually use the formula to help us find sort of like a mole to mole relationship. And like I said, if it breaks apart into 1-to-4, you'd multiply by 4, 1-to-2, multiply by a 2, and that will give you the concentration of just the individual ion. And obviously for our calcium here, it was a 1-to-1. So basically we multiplied that guy by 1. Any questions on concentration ions? Yeah, we typically see this with ionic compounds, because ionic compounds typically are the ones that will sort of make solutions, because when they go for a swim, they're strong electrolytes, which means they'll break apart into the ions. So really in solution, for example, if you had a solution of either one of those things up there, none of them would be together. So it would be 100% the ions floating around this solution. So we typically use it for that. You wouldn't necessarily be able to use sort of this relationship for something that doesn't break apart into ions, because it stays together. So there's no like breaking apart and figuring out it's like a 1-to-1 or 1-to-2 relationship. So typically we use this for ionic compounds or an ionic compound solution. So other questions? All right, well, let me try one here. Calculate the molarity of a solution prepared by dissolving 15.6 grams of KBr and enough water to make 1.25 liters. I'm going to give you some info that might be helpful. Our good friend potassium on the periodic table, 3910. And bromine, 7990, I'm going to go with. Sounds good. All right, so we're looking for the molarity. We're looking for the moles per liter. So give it a go, see what you come up with. That is obviously the hint. You need the moles and the liters, right? So take a minute or two to see what you come up with. So let's take a look. So obviously we're calculating molarity here. So we want to start with what molarity is, which is moles per liter. We also want to think about, do we have any of that information up front? Do we have any of that information good to go? We do have the liters part, right? So that is like good to go. No necessarily need to do anything with that number. We do not have the moles part, right? But we do have grams, right? How do we go from grams to moles? Grams to moles, we use the molar mass, right? From the periodic table, that's our conversion factor to go from grams to moles. In this case, it's KBr, so we actually just need to add these two together. And that would get us basically 119 grams per mole would be the molar mass of KBr in this case. So we could take the grams, which is a very common thing you have to do in these type of problems, is convert grams to moles. So as we talked about in whatever chapter that was, 7, I think, we do grams to moles using the molar mass. So that's where we want to start here. We're going to take our 15.6 grams of KBr. Just like we did in that chapter there, grams are going to go on the bottom. which always keeps the number. Up on top will go moles, which will get us to what we're looking for. The grams here will cancel each other out, and that will get you a 15.6 divided by a 119. We'll go with 0.131 moles of KBr. Is that the answer? That's not the answer. It is just the moles. And again, that's a very common mistake that people make. They box that thinking they just did it, right? So this is really just the top part, which now we basically have both parts that we need. So we can go into here and go with the molarity is moles per liter. And this would give you 0.131 moles up on top. This will give us our 1.25 liters on the bottom. And if I didn't hit clear on my calculator, we'll try that again, 0.131, 125 on the bottom. Going to get us a 0.105. Now, in terms of units, they really do not cancel out. So there's really two ways that you could kind of give this answer. You, again, can leave the number with the moles, and it is per 1 liter. So you could write it like that, moles per liter. And if you want to make it really fancy there and actually put KBR, you could do that as well. The other way you could do is at this point, once you've got your answer, which is moles per liter, you can write it with just the big M if you choose to do so. And again, that represents moles per liter. So you could just do 0.15 big M KBR. Either way is acceptable. I personally will usually just leave it like that, but if you want to convert it back the other way, that's perfectly fine as well. Any questions on any of those steps there? Okay. So here's just a sort of graph with some of the different concentrations we talked about. Obviously, we did percent by mass, percent by volume, mass to volume, and molarity here of our solutions, along with our solute and solvent, which make up a solution. So the next thing we're going to talk about is another example. That's a good thing to talk about. What is the mass in grams of sodium nitrate that's required to make 2.5 liters of a 0.15 molar sodium nitrate solution? So we're looking for grams. I'm going to give you some numbers here. Sodium 2299, nitrogen 1401 from the periodic table, and our good friend oxygen 16 here. All right, let's take a few minutes here, see what you come up with. We're looking for how many grams would be needed to make this solution here. Okay, let's take a look at this particular one. So let's say you read this problem and you're not really sure kind of where to begin. So we can kind of pull out the information. It'll probably hopefully lead us in the right direction. So we are definitely looking for grams of sodium nitrate. We obviously have some liters given to us, and we also have a molarity given to us, which right off the bat should tell us we are dealing with molarity, which is moles per liter, right? Now, if we just mark off what was given to us, we clearly have the liters given to us. We clearly have the molarity given to us. So if you weren't sure where to go next, probably a fairly safe bet, right, would be to solve for what you don't have, right? In this case, which is moles. And that does make sense because ultimately we want to get to grams. And as we just talked about, we could go from moles to grams using the molar mass from the periodic table. So, if you kind of know the formula, kind of see what's given to you, oftentimes points you in the right direction as to where you could go. You could rearrange that, and the moles would equal the liters times the molarity. Now, as I mentioned before, personally, I take more of a dimensional analysis approach to doing these calculations, and we can turn that molarity into 0.15 moles per liter of really sodium nitrate. Or again, if you needed it the other way, you could have liters up on top and 0.15 moles there on the bottom, not moles. So clearly we have our liters, which is what we want to times the molarity by. So we could start with our 2.5 liters, and we could see here now that we could kind of see the liter unit. We do want to use it like we see here on the left, which would be 0.15 moles per liter of sodium nitrate. The liters here will cancel, and we will end up with 2.5 times 0.150, 0.375. Now the units here are moles of sodium nitrate. First off, any questions on that part of the calculation? This is not our answer, right? Because we're just in moles. So we do need to do one more conversion, which is take our moles to grams. And again, it is the molar mass from the periodic table, right, that allows us to do that. So we need to add up all the parts here for sodium nitrate. So we got one sodium, that is 2299 grams per mole. We got one nitrogen, which is 1401 grams per mole. And we have 3 hydrogens, which are 16. So remember, we just basically add up all the parts to it. And I believe 85 grams per mole on that. Yes. And again, we could use this to do the final step here, which is take our moles into grams. And in this case, we could also approach it more like dimensional analysis. We see moles on top, which means moles need to go on the bottom so they properly cancel. 85 grams would go up there up on top. The moles would cancel. And 0.375 times an 85 gets us approximately 31.9 grams of sodium nitrate in this particular case. Any questions on that part of the calculation there? So what does this really mean? If you wanted to make the solution yourself, if you were in lab and you decided you want to make this solution, you would grab the bottle of sodium nitrate, you would go to the balance, you would measure out about 31.9 grams of it. You would take some deionized water and dump the 39.9 grams in it and basically get it to dissolve and use enough deionized water until your final volume is 2.5 liters. And at that point, you would have a solution that has a molarity of 0.15 molar. Any questions on any parts of that there? All right. By the way, if you are going to convert into moles, kind of like what we did in this problem, you always need to make sure that the volume is in liters when you're dealing with molarity so that it cancels out correctly. So very commonly, you're given a lot of times volume in milliliters. So the milliliter to liter conversion is used a lot with molarity. But you definitely want to always make sure volume's in liters if you're going to kind of multiply it or use it with molarity. So again, that the liters part cancel out. You'll sometimes see people use milliliters with it, which is fine, but you actually don't get moles. You get something known as millimoles. So you got to make sure it's in liters. Yes, sir.
Will we be deducting points for example, 0.150 moles? We just write that instead of 0.150 over 1 liter.
So say it one more time. For which one?
For the 0.150 mole.
Uh-huh.
And below you have another box of 0.150 mole over liters.
Uh-huh.
If we don't write with the liters, would we deduct the points or anything like that?
If your question is if you left it in molarity and did the calculation, no, you wouldn't get marked off wrong if you did it correct. My concern is, like I said before, a lot of times people forget all about the liters, not sure where it is. So if you want to be on the safe side, I would probably lay it up like that so you can see it. But technically, it's not wrong. Technically, you could just take 0.25 liters times it by the 0.15 molar, as long as you understand what that big M represents and get the right sort of units at the end. As long as you ended up with sort of these units at the end of that part of the calculation, then that's fine. Other questions? Okay. So here, if we wanted to look at the concentration of each of these ions, this is what we sort of touched upon a little bit earlier. So again, if we had, say, a solution of 1.2 molar sodium sulfate, and we were interested in the concentration again of the individual ions in that solution, not the whole thing together, we would want to look at it and make sure we break it apart correctly. So in this particular case, this would break apart into 2 sodium ions and 1 sulfate. And really the quickest and sort of easiest way to kind of turn the molarity of the whole thing into each of the ions is what we talked about last time or earlier today. We could see just clearly it is a 1-to-2 relationship between the sodium ion and the whole thing. So basically what that essentially means is you're just going to take 2 times that concentration, and that would get you 2.4 molar. And that would be the concentration of the sodium ions. Again, I did that big calculation earlier, and that's really what you end up doing is just multiplying by 2. So again, that's a very quick way to turn it from the whole thing into just the sodium ion. What would the sulfate concentration be? It is a 1-to-1 relationship, right? Which means if we multiply the original concentration by 1, we end up with the exact same number, right? So the concentration of the sulfate here would be 1.2 molar in there. Again, we get basically, if you want to think about it, twice as much sodium for every sulfate that goes into that solution. So it's twice as concentrated with sodium than sulfate. And that's what we see with the numbers, right? The number is basically twice as concentrated as the sulfate ions that are floating around that solution. We can do the same thing here with this guy, the 0.75 molar K2CrO4. When this breaks apart, that's potassium chromate. Breaks apart into a couple of potassiums and a chromate that has a -2 charge. And same thing here, if this is 0.75 molar for the whole thing, when we look at the relationship between the whole thing and potassium, it is a 1-to-2 relationship. So if you were just interested in the potassium, we would take 2 times 0.75 molar, giving us a molarity for the potassium of 1.5 molar. And if we look between the whole thing here and the chromate, it is a 1-to-1 relationship, which means, again, the concentration of the chromate here would actually remain the same. Again, as I mentioned before, concentration is not really additive. Obviously, if you add 1.5 and 0.75, you don't get 0.75, but it is sort of related to the proportion of the ions that go into the solution. Same idea here. We basically get twice the amount of potassium as we do chromate. So in terms of the concentration of the potassium ions that are floating around in that solution is twice the concentration of what we see for the chromate. Any questions on molarity here? Okay, we're going to lay it up there and